Welcome back to section 22. In this video we're going to solve a second order circuit that has been being forced by an exponential forcing function. So one thing to notice about this problem is our passive elements, so our capacitor, resistor, inductor, they are not in series or in parallel, and we're going to have a little bit of a challenge here. So our strategy should be, we want to write some equation that has our three passive elements in there if we can. More importantly, we want to find the voltage across this capacitor. So we'll label it that way. So we're looking for this V of C. That means if I do a voltage loop anywhere, I'm going to lose that. So we're going to end up doing currents. So we're going to say in the current through here, probably the current down and the current down. And then we'll just put those currents together, and then the V's will be what's left over, because again, I equals C dV dt. Alright, so let's look at that. So here's our problem rewritten. So I've divided my paper in half. This is a little bit longer of a problem. So we're going to mark that we have some voltage V here, some voltage Vs here, and we have our V of C across our capacitor. I'm going to assume that I have currents going this way, and this way. I'm going to do my KVL at V. My ground's down here. So we'll do a KVL at node V. So going in will be the current through the capacitor. So remember that is I equals C dV dt. I equals V over R, and I equals 1 over L integral V dt for our equations that we're going to be using here. So the capacitor in will be C, which is just a 1, and then dV dt, so we're going to do dVC dt, and then going out we're going to have those two, so we're just going to have, so this is not V of C through these things, this is just V. So we're going to get a V over R. So R is 1/3, so we're going to end up with a 3V for the resistor. And we're going to end up with a 1 over L, so a 2. So 1 over 1/2 is 2. Integral V dt. So remember, this is VC here. And then the thing across these two is voltage V. I'll label that here if you need to, but we already have the node there and there. So I want to get all of this in terms of one variable, ideally V of C, the voltage across the capacitor. So I need to do a substitution. So for that substitution, let's do a quick KVL around 1 here. So if I go minus Vs plus Vc plus V equal to 0. I want to solve this in terms of, so I want to sub out V. So I want to solve this for V. So V is equal to Vs minus Vc. So that's one I'm going to sub into this equation. When we do that, we'll get 1 dVc dt equal to 3 quantity Vs minus Vc plus 2 integral Vs minus Vc dt. So now everything is in terms of Vc. Vs is just a number or a function that I know, so that's not a big deal. So now I want to clean this up, so I need to get rid of this integral. So we're going to take the derivative of both sides of this thing. And then we're going to get a second derivative for Vc on this side. So this becomes 3Vs, and so we're going to get a derivative of 3Vs, a derivative of 3Vc, and this will become 2Vs and minus 2Vc. So let's clean all that up one last time. And we will end up with, so our highest order derivative is this one here. So that's going to be the first thing we're going to write down. And then I'm going to go collect all of my VCs. So I have a VC here and a VC here. The VS's I'm going to leave on this right side. So we're going to add over that one. So we're going to get plus 3. And we're going to get a plus 2. And then on our right hand side, we're going to get a 3 DDT VS, and then plus 2 VS. So now we have our differential equation. I'll box this because this is important. We're going to use this. So we know that V of C, when solved, will take the form V particular plus V natural. And we just need to find the form of V natural, find V particular, find our constants A1 and A2. That's the strategy. Let's start off. Let's go ahead and find V natural. So our natural response, so we have S is equal to a 3 plus or minus square root of 3 squared, which is 9, minus 4 times 2, which is 8, all over 2. So I'm just pulling those numbers. I have a coefficient of 1, a coefficient of 3, coefficient of 2, just pulling that down here into quadratic form. When you solve that, you will get a -2 and a -1. Alright, so those are real, those are distinct, so we're going to have an overdamped case. So that means V natural is going to take the form of A1e to the S1t plus A2e to the S2t, and you can pick whichever one you want, so I'm just going to pick 1 for 1 and 2 for 2. Doesn't really matter which is which. Alright, and then these A's, I can't do anything with them until I get the particular response and the initial conditions. So we are done with this for the time being. So I'm just going to rewrite our equation as we know it so far. So VC of t is going to be, so I'm just going to bring this thing back down and rewrite it. So VC of t will be V particular plus A1 e to the -1t plus A2 e to the -2t, and then for t greater than 0. Alright, let's go back up to the top here. So now, we need to find V particular. That's the next thing we can do. We can't find those constants A until we have everything else. So V particular, we would like to do substitution, if we can, but I need to know what VS looks like. So let's find our right-hand side. So RHS is just our right-hand side, or you can call this G1, whichever one you want. So 3 times the derivative of our function. So we are at, so this is t greater than 0. So that means we're going to have 3e to the -4t, because our step function u of t will be on. So I'm just going to put 3e to the -4t in here. And then we're going to put plus 2 times 3e to the -4t. And then we'll just simplify this. So this is what is on the right hand side. So we get 3, and then that ddt becomes a -4, and then we get 3e -4t over here, and then we're going to get 6e -4t over here, and then we'll simplify that and get a -30 e to the -4t. Alright, so that means that S particular is -4. And if I come back down here and compare, -4 thankfully doesn't match -2 or -1, which means we can use substitution and we will not have to use integration to find V particular. Alright. Oh, I guess it's an important thing here. I don't know if you picked up on it. We do take the derivative of our function because that's how the math worked out. So we're going to use substitution. So we're going to take this thing, push it up here. So we're going to end up with a -4 squared V particular plus 3 times -4 V particular plus 2 V particular equal to, so I'm not going to rewrite this right-hand side because I've already solved for it. It's just a negative 30 e to the negative 4t. So you combine all of these and you get 6 V particular is equal to a negative 30 e to negative 4t, which means that V particular is 30 over 6 is 5, so negative 5 e to the negative 4t. Alright. So now we can bring our function back up and write it in full. So now VC of t will be negative 5 e to negative 4t plus a1 e to negative 1t plus a2 e to the negative 2t for t greater than 0. So now all we have left to do is find our constants of integration, a1 and a2. Because this is underdamped, we're going to have to do simultaneous equations. In the other cases, we would find a1 or a2 instantaneously with our first one. So we would like to find the easy one, which is what is VC at 0 plus? Well, it's going to be the same thing as VC at 0 minus because it is a capacitor. Capacitors, because of the derivative here, cannot change instantaneously. I can't have a delta V without a delta T. So 0 minus 0 plus both basically mean right before and right after 0. Again, like if you kind of drew the curve, it would be a discontinuous point on that curve. So I'd be like, oh, here's our switch. I have right before, they have to share the same point. Otherwise, you get weird stuff. Fortunately for us, this thing was powered by a step function. That means at time before 0, this wasn't powered. So if you go through, you're going to find that V particular is 0, which means that there was no voltage on here, which means there's no voltage, there's no currents, no nothing before time equals 0. So that's just 0. So we'll plug that in, and we'll say that VC at 0 is 0. So we're going to get negative 5 e to the 0 plus a1 e to the 0, which is 1, plus a2 e to the 0. So that's equation 1 right there, which is that a1 plus a2 is equal to 5. So we'll come back to that in a second. I need to get a2. To get a2, we're going to come, so again, we want to use dv dt this time. So we want to take this equation and take its derivative. So we say dvc dt. It's the same pattern as we've done before with the unforced. So now we're going to get the derivative of this is a positive 20, because you just take the derivative of each piece here. So 20 e to the negative 4t. This becomes a negative a1 e to the negative 1t. This becomes minus 2, bring the sign with it, minus 2a2 e to the negative 2t. So there's our derivative. Not too bad because I don't have that sine or cosine function inside of there. So that is an advantage here. We are going to do this at 0, so we can go ahead and say that we want dvc dt at 0 plus. So that's just going to be 20 minus a1, because all these t's are going to go to 0, and then minus 2a2. So I just need to know what this is. It may be 0, it may not. So let's go find that. So to find the derivative VC dt at 0, we go back to our original equation, which was our KVL. You almost always come back to this original equation. So this is if I rewrite this equation in the generic form, we have 1 dvc dt, there's our dv, and then equal to 3 times v. Well, the voltage at 0 is 0, so 3 times 0 is 0. Remember, we're doing all this at 0. And then this term, we don't want to actually do the integral. This is the current through the inductor. The current through the inductor has to be the same after 0 as it is before 0. So this is for t at 0 plus, just to be clear. So we're going to get 0 because IL 0 minus is equal to IL 0 plus, which is 0. So that's what that is. Again, because we were done a favor, and this didn't have any power initially because of the step function. So therefore, dV dc, the derivative of the voltage or current is 0. So we say that dVc dt 0 plus is 0. We bring this equation back down. We put a 0 here. 0 equals 20 minus A1 minus 2A2. And we now have an equation that says that A1 plus 2A2 is equal to 20. That's equation 2. So now I have two equations with two unknowns. We can solve those however we want. So I'm going to write this back on the back and then we'll finish up. Alright, so I've just rewritten our equations here. So all I'm going to do is just subtract these two equations from each other. Our A1s will cancel out. A1 minus A1. This will become a negative A2, because 1 minus 2 is negative 1. And then 5 minus this is a negative 15, which means that A2 is 15. And if I plug that back into either of these two equations, I will find that A1 is, we'll get a negative 10 here. So rewriting our equation, we will get that Vc of t is equal to negative 5 e to the negative 4t plus, minus 10 e to the negative 1t plus 15 e to the negative 2t for t greater than 0. Unfortunately, this answer is wrong. Why? Because back previously I made a mistake. So let's fix that mistake. So we have, so this one's fine. Let's go find this one that's wrong. So we find the derivative here. We're fine here, 20 minus A1 minus 2A2, that is fine. The error comes in right here. So the current is 0. We do have dVc dt 1. That's fine. The issue is here. So I put a 3 times the 0. But if you notice, this is not Vc. This is V, which is the voltage across an inductor and the voltage across a resistor. Those are both allowed to change instantaneously. So just because it is 0 ahead of time does not mean it is 0 afterwards. So what is V equal to? Well, we know that V is equal to Vs minus Vc. We know Vc is 0. That can't change. So therefore, this is equal to Vs at 0 plus. So what is Vs at 0 plus? Well, let's go back to our function. And our voltage source is a 3e negative 4t. So if I put in a 0 here, Vs is just 3. So I'm actually going to get a 3 here, which means that this is not equal to 0. Instead, it is equal to 9. So I now have a 9 over here. And instead of being equal to 20, they are equal to 11. So you bring all that back over. And now you get that this is 6, and you'll get that this is negative 1. So our corrected response should be equal to 5e negative 4t, so that's our particular response. And then for A1, it is a negative 1, so it is minus 1e to the minus 1t. And then we're going to get plus 6e to the negative 2t for t greater than 0. So that is our answer, and this one can go away. Alright, so again, I know a lot just happened, so I'll just walk you through it real quick in case you kind of got lost. So you're given this circuit. We were asked to find the voltage across the capacitor for time greater than 0, so we wanted a response. We wanted basically a function of t. So to do that, we set up a KCL because we have I equals C dVt, C times dV dt. Our voltage across our capacitor will stay in our equation. If we do a KVL, then it will disappear, and I will have to find other ways to get it out. So I wanted to do KCLs if possible. And so I chose to do KCL up here at this node. Yes, we could do KCL over here, but I don't know the current through that resistor, through that voltage source. So this just seemed easier. So we did our KCL. We ended up with a voltage capacitance and then voltage. So these voltages are through our inductor and through our resistor. We needed to relate them back to VC, so we did a quick KVL through here, so minus Vs plus Vc plus V. And we subbed that V back in. And we did all of that to get a differential equation. Once we had a differential equation, we knew that the Vc in here, which is the thing we're trying to find, would eventually become a particular response. So what its steady state response, plus its natural or harmonic response. So what's going to kind of make it bounce. So why it doesn't instantaneously go up to its particular response. We then went and found the roots so we could figure out what type of natural response we had. So we had -2 and -1. That means it was overdamped, and it was going to take the form of AE to S1T, A2 E to S2T. After we did that, we couldn't find A1, A2 without finding a particular response, so we went and found the particular response. In order to do that, I need to know what the right-hand side looked like, because I need to know what SP was. SP was -4. We found that by just solving the right-hand side of our differential equation. Found that it was -4, did a substitution, and did some math. Once we had the particular response, we now had a function that looked like this. We needed to find A1, A2, so we plugged in our zeros for that. So we noted that initially the circuit was turned off, which meant that voltage and current were initially 0 in the circuit for every element, which means that Vc was B0 because this capacitor can't change instantaneously due to the derivative. I got this equation. Then for our second equation, since I have two unknowns here, I need a second equation. We're going to use the derivative of our function. So we took the derivative of this and got this. I needed to know what the derivative of the voltage was at 0 plus, so right after the switch. To do that, I went back to my original KCL equation, moved my dVcc down, noted that the current through the inductor was 0, and then for 3V, the first time through I messed this up, but the second time through we noted that this is V and not Vc, so this is not 0. Instead it is Vs minus Vc, so this part's 0, so that means it's Vs. So the Vs here we found by going back in and saying, oh, 3e to the 0 is 3. So therefore, dVc dt is just 3 times 3, which is 9. We then combined this and this together to get that 9 is equal to 20 minus A1 minus 2A2. We got some simultaneous equations, solved them. Sorry, it's a little blurry. There we go. And eventually got to our answer. So hopefully that helps. If you have any questions, feel free to reach out.